Oh, our last skills video and this monster learning unit that has been complex ionic aqueous equilibria. So now we're going to talk about sparingly soluble salts. And I'm going to apologize that I lied to you in Gen Chem 1. Remember this table back from Learning Unit 4 where we had these solubility rules? That's when we first started learning about acid-base chemistry and precipitation chemistry and redox chemistry. We're going to expand on all three of those in Gen Chem 2. Well, we've expanded a lot already on acid-base chemistry. Now we're going to expand on that precipitation chemistry. So we had this table here that indicated here's some things that are soluble, but we talked about here things that are insoluble. Okay, so for example, if we look over here, it says all common fluorides are soluble except those of lead and group 2A. So we knew from Gen Chem 1 that lead fluoride was insoluble. Well, the truth is it's what we call sparingly soluble, and we can write an equilibrium equation to show us that it doesn't completely dissolve, but a little bit of it does. So just like we did anytime we had an equilibrium before, we can write an equilibrium expression. The equilibrium expression here is going to be called KSP, and that SP stands for solubility product. So we're multiplying together the solubility of the ions that we have. So in this case, we're going to have lead and then fluoride, making sure we remember to square it. So as we get to the end of this learning unit, we've actually spent most of learning unit 6 on acids and bases, and then most of the beginning part of learning unit 7 here on either buffers or titrations, dealing with stoichiometry and coefficients that were generally 1. So we have to make sure we get back into the mindset of looking at our balanced chemical equation and understanding that sometimes we are going to see non-unity coefficients here, which means we're going to have exponents that we need to consider in our equilibrium expressions and x's that may have a 2, a 3, or even more than that in front of it in our ICE tables. But we're going to use a lot of the same strategies that we had with equilibrium problems all along here to think about solubility equilibrium problems. Just a little side note here to think about sulfides. So here again we talked about all common sulfides are insoluble except those of group 1A, 1A, 2A, and then ammonium. So one of the things that we need to think about is if we've got sulfide in solution, there's an equilibrium that we can think about. Because sulfide is a pretty strong base, it's the conjugate base of a weak acid, any chemistry in water is going to generate hydroxide and HS minus. So we have this equilibrium that we need to think about. So for example, if we had manganese sulfide here, not only is this sort of a sparingly soluble salt that it has this initial equilibrium, but we're not going to write S2 minus. What we're really going to have, and let me highlight this so it becomes clear, even though you might want to write this as S2 minus, that S2 minus that we might have here really needs to be written as these guys. So we're not going to see and we're not going to use S2 minus. That doesn't really exist. It exists as HS minus and OH minus. So just a little extra trick there if you have an insoluble sulfide. All right. You need to know your salts. You need to know how to name your ionic compounds. There's Quizlet flashcards that are available through Blackboard. If you didn't learn them in Gen Chem 1, you need to make sure you learn them now, because otherwise it's going to be kind of crazy trying to work through so many of these problems if you don't know their names, because you're going to see a lot of problems that just give you a chemical name, not a chemical formula. So you need to make sure that you're good on those. All right, so these problems that we're going to work through are kind of like the equilibrium problems that we saw when we introduced them in Unit 5. I'm calling them Type 1 and Type 2. Type 1 problems are where you're solving for an equilibrium constant. Type 2 problems are where you're given that equilibrium constant and you're solving for those unknown equilibrium quantities. And just like we saw, I took this slide right from Unit 5, how difficult problems are depends on how directly all of this information is given to you. So same strategy that we saw. This is again a modified slide from Unit 5 to show you, hey, we've learned a lot of this already, but I'm highlighting the things that are kind of new here. The first step is writing a balanced chemical equation. So this is where we need to think about some of this new information. What is the salt that we have and what does it dissociate into? Highlighting, you need to know the names of your salts. You need to take a chemical name, translate it to a chemical formula, and write a corresponding chemical equation. Second step, right? These are the steps that we've already learned, right? An equilibrium expression. This time is going to be KSP, highlighting that we tend to see non-unity coefficients, things that are not 1. So make sure you keep track of those. Make sure those coefficients become exponents in your equilibrium expression. Making sure units are species are in the right units. We're going to tend to see molarity here. Create an ice table, solve for X. All of this is the same. We're going to see those same simplifying assumptions, all of that good stuff again. Substituting back in. Well, a lot of what we've had in Unit 6 and the beginning part of Unit 7 is our ice tables, and solving for X was giving us something related to pH. Now our X is going to be giving us information about solubility. So making sure we answer the question in the prompt that was relevant when we were talking about pH, and was X equal to H plus or OH minus. In this case, we need to make sure we answer the prompt. Okay, so I'm going to address that in just a second here. Type 1 problems, pretty straightforward. We're again going to be determining KSP. They will either maybe give us concentrations of ions in solution, and we just need to calculate KSP, or maybe we need to have an ice table. You know, we did a lot of problems like this in Unit 5, similar kinds of problems here in Unit 7. So highlighting, making sure we answer the prompt. A lot of problems with KSP that are equilibrium problems ask you to determine the solubility of. And there's 2 things you might be asked to determine the solubility of, and that determines how you're going to use your X. So let's take our lead fluoride example here. If it is asking, what's the solubility of lead fluoride? It's basically asking you for your value of X. That's pretty straightforward. If it's asking you for a specific ion, they're really asking you for the equilibrium concentration of that species. If they're asking it for lead, that is X. But remember, if we had an ice table here, this would be 2X for fluoride. So whatever your X is, we need to double it to get our solubility of fluoride. So just make sure you're looking at answering the right prompt. Is it asking about the ionic compound that you started with, or is it asking about one of the ions? Okay, you'll need to use X differently in that way. All right, last little piece here is to say, well, there might be a third kind of problem we have here, which really wasn't relevant when we were talking about other kinds of chemistry. And this is also talking about formation of precipitates, okay? So this has to do with doing a Q versus K comparison. Okay, K represents the maximum allowed concentrations of ions. That's where we want to be at. This is the maximum solubility. If Q is equal to K, I'm going to be saturated. I've reached my limit. Okay? If Q is greater than K, I've exceeded my limit and precipitation is going to happen. If Q is less than K, I'm actually below my limit. I could put more salt in solution and still not be at my maximum capacity. So we are going to see Q versus K comparisons. I know some questions came up with acids and bases. Do we see Q versus K? Not so much there, but we do see Q versus K with solubility, because if we've exceeded our solubility, we're going to form a precipitate. If we are at our solubility, we're saturated, and if we're below our solubility, we actually could dissolve more in solution. So we may need to think about doing a Q versus K comparison. So that's sort of a third kind of calculation that we could see here. The other thing to think about is more from a qualitative standpoint. Remember when we talked about Le Chatelier's principle, and we talked about sort of a push-pull analogy to think about shifting equilibria? Well, the same can be true with salts. So this is basically taken from Unit 5, but it's to remind you that a pull means we're removing a reagent and we're going to shift the equilibrium to that same side. We're going to pull it close. A push means we're going to add something into our equilibrium, and we're going to shift the equilibrium to the opposite side. We're pushing it away. Okay, so again, addition of a reactant will push the equilibrium to the right. Removing a reactant pulls it to the left. So we can use the same principle to affect solubility, right? So there's two ways that we can think about doing this. The first is what we call a common ion effect. Okay, so we actually talked about this, or we saw this in acid-base, but we really didn't think about it from a Le Chatelier's principle. So let's imagine here that we've got this weak acid here. If we've got this weak acid and we also add the conjugate base into solution, because we're adding in something on the right side, our equilibrium will shift to the left. It actually means that less of this acid gets to dissociate and lose its proton, become deprotonated, because this pot is already somewhat full. Okay? We can think about the same thing with solubility. If we were to add in our chromate ion here, if we added it in, for example, with a very soluble salt like sodium chromate, we're going to shift the solubility of this guy to the left, such that not as much lead chromate is going to get to break apart because we've already filled our chromate cup up. So we're going to see a decrease in the solubility of our lead chromate. We call this the common ion effect because we could add this ion in one of two ways. We could add it in from this guy dissociating, or we could add it in from a soluble salt like sodium chromate or sodium acetate. So Le Chatelier's principle kind of explains that, but we see it applied here to solubility. We also can think about this in a removal way. So the common ion effect is adding something in. We can also think about removing something. So we can, for example, think about increasing the solubility here if we added a reactive ion. Let's look at calcium carbonate. This is essentially what chalk is, or Tums tablets, right? The antacid. This is sparingly soluble, so we're going to have a little bit that dissolves. But if we were to add acid into solution, because acid is going to react with that conjugate base of a weak acid, it's going to generate bicarbonate. Okay? We add some more in, we're going to actually generate carbonic acid, and that's how we generate some fizz in that solution. But this is going to move this equilibrium towards the right because we're removing this carbonate ion. So removing that carbonate ion shifts the equilibrium to the right. With salt solubility, shifting the equilibrium to the right means we're increasing solubility, right? This is what happens with acid rain and limestone, right? We dissolve more limestone because the acid is moving this equilibrium to the right, okay? The theme that we see there with decreasing solubility that we saw on this slide here, the common ion effect, really is what decreases solubility because we're shifting that equilibrium to the left. All right, we can see this applied in what we call selective precipitation. So in this process of selective precipitation, and we'll have a couple of problems we can work through that practice this, what happens is, let's say we've got two ions in solution, and we're going to be adding, let's say they're two cations, two metal cations. Okay? And we're going to be adding a common anion that, let's say, precipitates both of those salts. Well, what's going to happen is one of them is going to precipitate out first because it is less soluble than the other. So we're dripping in our anion and we're going to reach maximum capacity, let's say for this guy first, and that selectively precipitates out a solution but still allows this guy to stay in solution. So this is kind of a really neat chemistry that allows for different things to be done to treat water, for example, and selectively remove certain ions. So the KSP of the less soluble compound is going to be exceeded first, and we're going to precipitate that one out of solution, but we're going to leave the other metal ion in solution. So conceptually, you reach maximum capacity of salt 1 before you reach maximum capacity of salt 2, and that allows you to selectively precipitate that. So all of this stuff with our sparingly soluble stuff was conceptual right now. There is an extra credit ed puzzle video that kind of walks through some of the computational pieces to think about with sparingly soluble salts.